Hello, welcome. Thanks for being here. Recently, we've been talking about calculating area under a curve between the curve and the x-axis. And in section 5.1, we were approximating area by constructing rectangles of an equal width and calculating the area of each rectangle, adding them up, and approximating the area. In 5.2, we introduced the notation of this definite integral, and we said that that definite integral will calculate that area between the function and the x-axis. So everything we've seen so far, our function is always positive, which means it's always above the x-axis. No part of the graph goes below. Okay, but what happens? Not every function is positive for every value in its domain. So what we need to do is take a look at that today and see what happens. All right. One thing to point out is that we must have this requirement here that A is less than B. We always talk about A being smaller than B. Okay, A could be negative and B could be positive, but it's always A represents the number on the left of the area. Okay, so here's a function. We want to approximate the definite integral from 0 to 3 of 4 minus x squared using n equals 6 or 6 rectangles. So here's my graph of the function f of x equals 4 minus x squared. So parabola, it opens down, and we can see that part of the parabola is above the x-axis and part of it is below. Okay, so let's see what happens when we calculate the area of this function on this interval. So first thing we need to know is if we're going to have 6 rectangles, what is the width of each rectangle? So that's our delta x. So remember, it's our b minus a. B is 3, a is 0. So we basically have a distance of 3 from beginning to end, and we're dividing it up into 6 equal parts, 6 rectangles. So we get 3 over 6, which leads us to our width of each rectangle is 1/2. Okay, so when we've calculated or approximated our area, we needed the function values for our height. So what we're going to do is we're going to plug in our values. So we're starting at 0. And remember, you just keep adding the width. So you're going to add 1/2, add 1/2 until we get to 3. So we'll get all of our x values in that interval. So 0, we add 1/2, or we'll use 0.5. And then 1, 1.5, 2, 2.5, and then 3. Okay? So when we substitute those values in to our function, we get, well, if x is 0, we get 4. That one's pretty easy to see. At 1/2, we get 3.75. If I plug in 1, 4 minus 1 is 3. 1.5 is 1.75. Plug in 2, 4 minus 2 squared is 0. Plug in 2.5, we get negative 2.25, and plug in 3, 4 minus 9 is negative 5. So right here, I see something that I've never seen before. We've never seen function values that were negative, okay? So what is that telling me? That means when we use these height, we're saying that our height is negative, okay? So that's going to give us a negative area for those rectangles. Okay, now I'm going to draw the rectangles at least one time so you can see it. So if I do a left-hand approximation, then I'm going to draw my rectangle so that the left value of each interval, that's where the height of the rectangle is. So here's my first one. And at 0.5, I'm going to go up here to the curve. That's the height of the rectangle. At 1, same thing. 1.5. Now look what happens when I get to 2. There is no height Okay, so if you think about that, that's the reason for this 0 here. Okay, my rectangle has a width of 0.5 but no height because the point is on the x-axis. All right, then if I go at 2.5, I go down here to the curve, and that's where I draw the height. So see what's happening is this rectangle is below the x-axis. So if I do the left hand, I have one rectangle below, but if I did the right hand, I'd have two rectangles below. So you can see what's happening there. Okay, so let's calculate our left hand approximation. So the width, which would be 0.5, times the sum of the heights. So we're doing left hand, so remember we're going to start with our left values. We're going to use these first 6 values. So I'm going to add these up. Okay, and that's going to give me 0.5 times 10.25, which is 5.125. So we're taking half of 10. Okay, see what happened here? With this height or function value being negative, we actually subtracted 2.5. Okay. Let's do our right hand approximation then. So if I do my right hand approximation once again with this a half, and now I start with the second value here, which would be the right value of the first rectangle. Okay, so add those up. Okay, so I get 0.5 times 1.25. So half of 1.25 is 0.625. Okay, so look what happened. This one is considerably smaller than this one. Well, why is that? Because I subtracted here 2.25 and I subtracted 5. Okay, so if I was drawing the right rectangles, then I have more area or more, because I have 2 rectangles below. So there's more area below the x-axis. All right, so of course then our best estimate would be the average. So if I average those, add up and divide by 2, I get 2.875, so approximately 2.9. Okay, and the exact area using a calculator is 3. The cool thing is you'll be able to find the exact area when we get to chapter 6. Okay, so look what we can see what's happening. We are subtracting the area that is below, of the rectangles below the x-axis, or we're adding a negative area. Those areas are negative, so it's whichever way you want to look at it. Okay, so now we're going to look at what happens when our function values are positive for some x values and negative for others, which means our function at least at some point goes below the x-axis. And we're still talking about a is less than b. Okay, what the definite integral does then is it counts the area above the x-axis as positive, the area below the x-axis as negative. So you can think of you're adding positive and negative numbers, or you can think of it as subtracting. So that means the definite integral calculates a number. Okay, how does it get that number? It takes the area above minus the area below. Okay, so I could come out with a positive number, I could come out with a negative number, I could come out with 0. But here's where we're going to have to switch our terminology. Definite integral now does not always calculate area. Okay? We basically just say it calculates a number, a value. Some books will call this the net area. Okay? But we do not talk about it as area. We just talk about it as a number. Okay? So let's take a look at another example. Let's evaluate 0 to 6, the definite integral 0 to 6 of the function x minus 2. So notice this is a linear function, okay? We can find the exact value if we're looking at area bounded by the graph of a linear function, okay? So because we can divide it up into sections that we know, okay? So let's graph that function. So if I'm going to graph f of x equals x minus 2 on the interval from 0 to 6, okay? And we're not even going to talk about rectangles because we don't need those. So if I start at 0 and I put 0 in there, I get negative 2. And if I put in 6, I get 4. So my y values go from negative 2 to 4. So here's a point. What happens if I put in 2? I get 0. If I put in 4, I get 2. And we know it's a line with a slope of 1, so you could use the slope and the y-intercept as well. Here's my function, the graph of my function. Okay, so what we're going to do is divide it up into sections that we can calculate. Basically, we've got this part, we've got this little section of area below. Okay, so if I look at the area of this region in red, I know that that's a triangle. So 1/2 base, and I could say my base is 2, my height is also 2. Base times height. So 1/2 of 4 is 2. So the area in this region below is 2. Okay. If I go above, once again, I also have a triangle. So to find the area of this region, I can once again find the area of a triangle. Okay. So this area, that doesn't look good. This area is once again 1/2 base times height. So here I can see the base is 4, and this height is also 4. So 1/2 of 16 is 8. Okay, so this region is 8. So if I'm finding the definite integral, then remember it's not necessarily finding the area, it's finding basically the area above minus the area below. Or we're considering this area down here below in the red to be negative. Okay, so it's the area below, which is, whoopsie, I'm sorry, I gotta write this down. Which is negative 2 plus the area above, which is 8. So negative 2 plus 8 is the same thing as 8 minus negative 2. So my definite integral evaluates out to be 6. Okay, so we just say the definite integral is 6. It's the area above 8 minus the area below 2. Okay, so we've got different terminology now. Now when we talk about total area, or just area in general, if they don't say total, it's assumed we mean geometric area. So the total area then of this is not giving the area below a negative value. So our total area is really just 2 plus 8, which is 10. Okay, so there is a difference, and we got to get used to that. All right, so what about total area? Well, total area will be the same as the value of the definite integral if my function never goes below. The function is always positive, okay? That will calculate the total area as well. But if the function is above and goes below at some point in time, then the definite integral is not the total area, okay? It just gives us a number, okay? So when we're talking total area, it will always be positive unless, of course, my function is f of x equals 0 or y equals 0, then there is no area between the function and the x-axis because the x-axis is y equals 0, okay? So the big thing to keep in mind is that a definite integral comes out to be a number. It can be a positive number, it can be a negative number, or it can be 0, okay? So if it's negative, then that means all of the area or more of the area is below the x-axis. So for example, if I want the definite integral from a to b of this function, then I can see that between a and b, the entire area is below. That's why it comes out to be a negative. Okay? If I want the definite integral from a to c, then part of the area is below, part of it is above, but there's more below. So when you take the little area up above and subtract what's below, you're still going to come out with a negative number, okay? If the definite integral comes out to be a positive, then that means more or all of the area is above the x-axis. So, for example, the interval from a to b here is positive. The entire area is above, so we get a positive value for that definite integral. Okay, and if I look at a to c, then part is above, part is below, but more is above. So when I subtract or take the top positive and add a negative to it, it's still going to be positive because the area above is larger. Okay, so there are situations where the area above and below is the same. So here, I don't know if you can tell, but it's an odd function which will give us the same area if we look at an interval that is symmetric about the y-axis. So if I look at this interval and I say integral and I say the definite integral from -3 to +3 of this function is going to be 0. Because let's say I knew this area. Let's say this area is, what would that be? 3 times, oh, we don't know without the function. I can't even approximate it. So I'm just going to make something up. Let's say that this area is 5. That means that this area would be -5. And when you add those up, you would get 0. Okay, so let's compare definite integral to total area. Okay, so here I've got a fun looking graph of a function f of x, and I've got a couple regions above and a couple regions or areas below the x-axis. So if I want to evaluate the definite integral from 0 to 9, which means from the very beginning to the end of this function, then what's going to happen? A sub 1 is my area, is my first area below. That region has an area of 5. So that means I'm going to consider that to be negative. So I've got -5 plus then my second area, A sub 2, is 16. So then I'm going to add 16. The next one is below, so that's going to be negative. So I'm going to be actually subtracting 7. And then adding +4 for the last region above. Okay, so that comes out to be, for my definite integral, I get 20 minus 12 is 8. Okay. The total area then is basically just adding up those areas or not thinking about them being positive or negative. For example, my first area, A sub 1, we could say that's a negative area. So the idea is if we considered it negative, we want to take the absolute value because we ignore the idea that it's below. So it would just be 5. Okay, plus 16 plus, if this area is 7 below, that would be considered a negative 7. But we'll take the absolute value, so we would consider that as just plain 7. And then the last region is above, so it has an area of 4. So when I add those up, I get a total area of 21 and 11 is 32. So there is a difference. Okay, now here's something kind of cool. So this is the graph of the function f of x. What happens when I look at the graph of the function, the absolute value of f of x? Okay, what that means is that's taking the absolute value of all the function values or the y values. So that puts all of my points above the x-axis. So any place where my original function was below, it is now above. All those y coordinates became positive. Okay. So if we're taking the absolute value of the entire function. Okay, so if I calculate the definite integral from 0 to 9 of the absolute value of f of x, then basically this region is 5, this region is 16, this one is 7, and this one is 4. Okay, so ultimately it is just 5 plus 16 plus 7 plus 4, which is 32. So what do we notice here? That here we said the total area was 32, which is basically the same. So when you're taking the definite integral of the absolute value of a function, that will be giving you the total area because you will not have any regions below. They will all be above, so every one will be considered a positive number. Okay, so now this is kind of an interesting situation. Here we're saying, okay, the absolute value, or excuse me, the definite integral of the absolute value of the function. That means we're taking all the y values, taking the absolute value, which will make them positive. That will give us the total area. Now, look at this is a different situation. The absolute value bars are outside of the integral, or the integral is inside of the absolute value bars. So when you calculate this definite integral, it could be a positive number, it could be a negative number, or it could be 0. So then you're taking the absolute value of that, okay, which it will come out to be a positive. Okay, because if you take the absolute value of a positive, it's positive. Absolute value of a negative is positive. Or it could be 0, which is neither. Okay, so be careful of the location of the absolute value bars. Two different things. Okay, let's look at one last example here. If you would like, you might want to pause the video and give these a try on your own, see what you come up with, and then restart it and check your answers. Okay, so I have a function graphed, and I can see that these regions, I've got the area here. Okay, regions above and below. So we're looking at this function on this interval from A to D. All right, so I want to find out what is the definite integral from A to B of f of x. Okay, well, that's basically my first region here. So it's 11 above. Okay, the definite integral from B to C. Okay, notice that that region is below, so that 9.5 is going to be negative. Okay. The definite integral from C to D Once again, region is above, so that definite integral is going to be a positive 6. Okay. Now, when I go from A to C, I notice that I've got from A to C, then it's the sum of those signed areas, okay, or top minus bottom, whatever you prefer. So basically we have 11 minus 9.5, and that's going to give us 1.5. So my definite integral comes out to be a positive number, 1.5, but it does not calculate total area. Okay. How about the definite integral from A to D? Okay. So I've got 11 minus 9.5 plus 6 comes out to be 17 minus 9.5, basically, is 7.5. Okay. And then the definite integral from B to D. Okay, so that I have a negative 9.5 plus 6. So I end up with negative 3.5 for the definite integral from B to D. Okay, so I end up with a negative value for that definite integral. Okay, all right, so now let's look here. We've got some absolute values going on. So we're still looking at this integral from B to D. Okay, so if I say the integral from B to D of the absolute value of the function, then basically what's that saying? From B to D, then this from B to C then would be positive. So it would be, if that was flipped up, and that would be an area of 9.5. So ultimately it's taking, we're looking at the positive area. So it would be 9.5 plus 6, which would be 15.5, okay? So that would be the total area on that interval from B to D, okay? So now I look at what's the absolute value of the integral from B to D, okay? Well, we just evaluated this. The integral from B to D, we said, is negative 3.5. So then we take the absolute value of that and we get positive 3.5. And there you go. I hope you enjoy these definite integrals in this area as much as I do.